So one final example of being able to utilize a Jacobian to evaluate a not so nice region for a double integral is, let's say we have a region that's bound by a square with the corners 0, 1, 1, 2, 2, 1, and 1, 0, and we want to evaluate x plus y squared plus n times sine square x minus y. Alright, so this is a pretty difficult problem, so hang in there for this one. Unfortunately, with this problem, unlike the other ones, we weren't necessarily given the equations of the lines. Alright, so what we might want to do first is to be able to find the 4 equations of the lines that constitute or that bound R. Alright, now some of them we can do very easily by inspection. Okay, for example, the first line that we have, let's just say it's the line that's connected by the points 1, 0 and 0, 1. Sorry about that. That's not too good there, but you can imagine that that's the point 0, 1. That's a pretty easy line to be able to see. Alright, so I'm just going to call that L1. And L1 is going to be given by the equation, we could say y is equal to 1 minus x. Right? If you don't believe me, you could certainly go through the equation of the line to be able to figure that out. Okay? Or another way to write that would be that line 1 is that x plus y is equal to 1. Right? I'm going to define this as line 1. Let's call this one line 2. Right? So line 2, we could do the exact same thing. And if we were to be able to evaluate that one, we could kind of extrapolate this and find that the intercept is going to be 3. I know for my graph it's not that good. So we could say that that equation would be 3 minus x. All right? And again, the points for this are going to be 2, 1 and 1, 2. Right? So, of course, if you don't believe me, you can substitute directly, and you can see that it does end up being y equals 3 minus x. All right? Or, in other words, x plus y is equal to 3. All right? So that's helpful. Let's call this one line 3. All right? So line 3 goes from the point 1, 0 to 0, 1. And it's obvious that each time x increases, y increases by 1 as well. Right? So one way we could relate that is y is equal to x plus 1, right? Or I guess we could say x is equal, well, we could say that y minus, or x minus 1, excuse me. And again, we could just substitute that very easily to find line 3. Or another way to write this would be x minus y is going to be equal to 1. All right, so what we could do is we could add 1, subtract y. And then finally for line 4, we can define, and I'm going to call it this line, line 4. We could say that y is going to be equal to, we could say x plus 1 in this case. Again, if you don't believe me, just substitute the points back in. Or we could just say that x minus y is going to be equal to negative 1. All right, so those should be our 4 lines that we're looking at. It's imperative that we get the lines, because once we have the lines, then we can have a substitution. So let's use the substitution, and I think it's pretty obvious that we have an x plus y and we have an x minus y. So let's let u be equal to x plus y. Let's let v be equal to x minus y. And what we're going to do is we're going to be able to find a transformation in terms for x and y. All right? So let's just add those together. All right? So we have these equations. We can add them together. And if we do that, we get u plus v is equal to 2x. And I'm going to skip down to the bottom here. We could divide that by 2. and we get that 1/2 u plus 1/2 v is going to be equal to x. And we're going to hold on to this because that's the first coordinate in our transformation. Now, we can solve for y readily because y is going to be equal to u minus x. So u minus x is equal to y. Or u minus the quantity of 1/2 u plus 1/2 v is equal to y. We could distribute and subtract, so we would end up with 1/2 u minus 1/2 v is equal to y. All right. We want to translate from the xy plane to the uv plane. Okay, so in the xy plane, remember we had our 4 lines. Okay, so we had x plus y is 1 and x plus y is 3. We also had x minus y was 1 and x minus y was -1. And what we'd like to do is we'd like to transform that into the uv plane. And if we do that, remember that u was x plus y, so we get u equals 1 and u equals 3. We get that v equals 1 and v equals -1. And so now we have all that information, right? It's very helpful for us to be able to evaluate because now we know the bounds, we know the transformations, okay? The only thing we need to finish this to be able to go in terms of u and v is we need a Jacobian, all right? So we are going to now find the partial of u, or the partial of x, excuse me, with respect to u. So we need partial x, partial u. We need partial x, partial v. We need partial y, partial u. And then we need partial y, partial v. Partial x, if we go back up top, with respect to u and also with respect to v, is going to be 1/2. So we get a half, we get a half. Partial y with respect to u, 1/2. Partial y with respect to v, -1/2. And so finally, our Jacobian is going to be equal to the absolute value of 1/2 times -1/2 minus 1/2 times -1/2. Right? And then we get -1/4 minus 1/4, so that ultimately should just be a half. All right, and that's our Jacobian. We're going to hold on to that. All right, so let's go all the way back up. All right, we have all this information. So we have x and y, okay, which we're going to hold on to. All right. And then we also have u and v. All right, and this is the more important part right here because this is what we're going to substitute back in. Okay, so we have our original double integral of some area A or some region R, doesn't matter, and it was x plus y square quantity, and I think we had sine of x minus y square, or sine square of x minus y dA. Well, now we can rewrite that completely in terms of u and v and make this a much more simplistic evaluable integral. Right? Going back up here, here's the bounds for u and v. Right? So that's pretty easy to see. So we're going to define the double integral from 1 to -1, or -1 to +1. And then we know that u is going to range from 1 to 3. Instead of x plus y, we have u square. Instead of sine square of x minus y, we have sine square of v. We also can't forget that we have the 1/2 from the Jacobian, and then we have the order du dv. This integral is actually a lot easier than the other ones that we've seen because u and v are completely independent of one another and all of the bounds are constants. So, factoring out the 1/2, minus 1 to 1 of sine square v dv, and then integral from 1 to 3 of u square du. All right, now to evaluate, all right, this is actually a pretty cool trick that we can use. We're going to use the power reducing formula on sine square. All right, so you might remember, and I'm going to write this off to the side, from calculus 2, sine square of v is going to be equal to 1/2 minus 1/2 cos of 2v. All right, so that's our formula that we're going to utilize. We're just going to substitute that back in. And so now we're going to get 1/2 integral negative 1 to 1 quantity 1/2 minus 1/2 cos of 2v. And we have dv. And we still have that integral from 1 to 3 of u square du. At this point, now we have very rudimentary integrals to evaluate, so let's get to it. So now we're going to have 1/2 quantity 1/2 v minus 1/4 sine 2v. All right, so don't forget, you have to use the reverse of the chain rule when you're integrating this. So now we have dividing by that extra 2 from the 2v. That's going to go from negative 1 to 1. And then a very simplistic integral, 1/3 of u cubed from 1 to 3. Okay. We're going to substitute. This might take a little bit to do. So now we're going to have 1/2 quantity 1/2 times 1 minus 1/4 sine 2 times 1. I'm going to put this in parentheses. Minus 1/2 times negative 1 minus 1/4 sine 2 times negative 1. All right, so that would take care of that. Bracket. Now we're going to multiply that by 1/3 of 3 to the 3rd minus 1 to the 3rd. All right, so getting a little bit ugly here, but hopefully it's just computation at this point. We have a 1/2 and a 1/3. Let's just make that 1/6 right away. And then we have 1/3 minus 1. That's going to be 26. So we can just end up with 26/6 right away. All right, so that just takes care of all this stuff that we have underlined. We have 1/2 times 1, which is a half, minus a negative 1/2, so that's a 1. Right, and that comes from 1/2 minus a negative 1/2, so that's where we get this 1 from. Right? And then finally we have negative 1/4 sine of 2. So we have negative 1/4 sine of 2 minus a negative 1/4, so it becomes plus 1/4 sine of negative 2. All right, so I'm going to write that out. So we have minus 1/4 sine of 2. This just becomes a plus 1/4 sine of negative 2. All right, and we could simplify that even further. All right, so here's a sneaky trick you might remember from trigonometry. So we have the 13/3 from the simplification. We have 1. And remember that sine is an odd function, which means that we can rewrite it by factoring the negative 2 out of it. Okay, just the negative can just come out front and turn into a negative 1/4. So and then we would have negative 1/4 sine of 2 minus 1/4 sine of 2, because again that's an odd function. And mercifully, I think the nicest answer we can get is 13/3 1 minus, we have a quarter and a quarter negative, so that's 1/2 sine of 2. It's probably the best answer that we can get out of this. All right, so now think about this. For as rigorous as this problem was, we'd have to do 2 more double integrals if we were to be able to evaluate this without using the Jacobian. So hopefully you understand the power of the Jacobian and how nicely it can be utilized to be able to evaluate these double integrals.